Thank you very much for having me. So as Mahmoud said, I'll be talking about aligning machine learning with society. So as we all know, machine learning is everywhere, influencing critical aspects of our lives, from finance, where algo trading dominates 80% of the US stock market, to robotics, targeted ads, vision, large language models, healthcare, and decision-making. Now, behind all of these remarkable achievements lies a fundamental skill. First, we take some training data, which is sampled from an unknown distribution D. Then we feed it into a machine learning algorithm, which outputs a model that maximizes accuracy on the training data. Now, when a new data arrives, we are assuming it's coming from the same underlying distribution D, and we get some predictions. And a critical aspect of this process is generalization, which connects the training accuracy with the performance on unseen new data. And this is very important. It's very important. I think I have an echo here. So sorry about that. So there are a lot of fireworks on that. I also worked on that, but this will not be my focus for today. Instead, what I'm hoping to convince you is that this process isn't as sterile as you might think. And instead, society is involved in every single step of this process. So here are some problems that are in the intersection of machine learning and society. And today I'll talk about, for the first topic, I'll talk about strategic classification. So these are three works that one of them also addresses fairness. And I'll talk about another work that addresses both personalization and explainability. But I also worked on incentivized collaborative learning and learning under other societal constraints. And there are other important topics such as privacy, accountability, and so on. And in general, my goal is to build learning-based models that are aligned with society. Okay, so I'll start with a quick research overview. And then I'll talk about strategic classification. Then I'll talk about this paper that addresses both personalization and explainability. And I'll mention some future directions. Okay. So let's look at some examples of how society both affects and is affected by machine learning. So first, we need the training data. And in order to get the training data, we rely on society. So we should incentivize society to provide us their data. So I worked on this in the context of multi-arm bandit and active learning, but I will not talk about these works today, so feel free to ask me about this later. Second, once we have our model, then we need to have the new data to have it from the same distribution as the training data, because this is going to be essential for accuracy. Now, this is not always the case, as individuals, once they see the model, they might manipulate their data to achieve favorable outcomes. And this is called strategic classification, and this will be my first topic for today. And finally, models should serve society. And we, as a society, care about more things beyond just accuracy, such as personalization, explainability, and fair predictions. And I'll mention these topics today. So in general, I'm interested in machine learning theory and societal challenges. And as such, all of my works can be found on different parts of this pipeline. Okay, so let's talk about strategic classification. So one observation is called Goodhart's law, which says that when you start measuring people according to some target, it ceases to become a good target, and it ceases to be a good measure and becomes the target. So let's look at some examples. First, in loan applications, in order to get a loan in the US, what you want is to have a good credit score. One way to improve the credit score is by, let's say, applying for an additional credit card. Now, of course, this takes time. Time costs money. But people still do it because they want to get a loan. And the thing is, it does not necessarily improve loan worthiness. So if someone has an additional credit card, it doesn't necessarily mean that they are more likely to return the loan. Another example is job application. So it starts when applicants might tailor their resumes in order to pass a screening software. And then once they are invited for an interview, they might memorize answers for the interview questions, for example, from LeetCode. Now, again, this takes time, but people do it to get a job. The thing is, it does not necessarily make them better workers. So now let's think about it from a strategic classification perspective. So this was introduced by Buchner and Schaeffer in 2011, and by Hart, Megiddo, Papadimitriou, and Wouters in 2016. Now, in machine learning, as I said, we usually have a model. So someone learned the classifier age, and we're going to assume this is a common learning. And our key observation here is that individuals will manipulate their features to achieve favorable outcome. So say we have an applicant, Stewie here, wants to get a loan, and his features are mapped into a point which is currently in the negative area of the classifier. So what Stewie might do is he might apply, let's say, for an additional credit card, improve his credit score, and get a loan, even though his loan worthiness hasn't changed. Okay, so more formally, we are thinking about binary classification, where the learner releases a classifier, and each agent is represented by a feature vector and a label. Now we're going to assume there is a distribution over the agents. And what the agents want is to get a positive prediction at a reasonable cost. So maybe applying for 1 million credit cards just to get a $1,000 loan doesn't make sense. And the way we are going to handle this, we are going to define a utility of agent X from manipulating to a different point X prime, or the same thing. And this is going to be 1 in case they get a positive prediction minus the cost of manipulation. So for example, and you can think about the cost as, for example, the L2 distance, and the best response is going to be the point that maximizes this utility. So for example, if you look at the figure here, and the cost of manipulating from X to the nearest point on H, so this will be a point that will get a positive prediction. Let's say the cost is 0.9, then the agent will manipulate because the utility will be 1 from the positive prediction minus 0.9, 0.1. This is also going to be the best response. If the cost would have been 2, then in order to get the positive prediction, the agent would have gotten a negative utility, so it doesn't work. Okay, now since we're thinking about learning, there's also going to be a utility for the learner. So generally, we are thinking about accuracy, but in this case, this is going to be strategic accuracy. So it's going to be the expected accuracy under the assumption that agents are going to best respond. Now, for those of you who are familiar with stackable games, this is exactly a stackable game where the first player is the learner who commits to a strategy, which is the classifier, and the second player is the agent who best responds. Now, once this entire process is over, the learner will estimate their accuracy, and if they find a better classifier, they will release a new. So for example, here, if the learner simply shifts the classifier by a distance of 1, and we know that in this example, the cost is the L2 distance, then every single negative agent is no longer incentivized to manipulate, and every positive agent is still incentivized to manipulate, and they'll get a perfect accuracy. Everything clear?
But you kind of force the positive agents to manipulate,
right,
even though they didn't have to.
Right, and sometimes this is life, right? Good students still do psychometry, right? Okay. But that's a good point, because this is like one of the things that I'm interested in working in the future. So I think this is a very interesting problem, but I also think that strategic classification is more complex than what we have here. And I was interested in pushing it forward in several fronts, so it would become more realistic and more up to date. So first I worked on what happens if the screening process is more complex. So for example, if we have multiple classifiers that the agents need to pass, but I won't be talking about this today. Second, I wanted to know what happens if the agents don't know exactly what is the model. Third, I wanted to know whether we can learn age efficiently, because I'm coming from a machine learning world. Sorry. And finally, I wanted to know what happens in the LLM era. So I'll talk about these three works today. And let's start with partial information, or what happens if the agents don't know the models. So in the classic setting, we assume that the learner releases a classifier and all the agents manipulate accordingly. Now, this is not always realistic. For example, when was your last job interview when the interviewer told you exactly what are they going to ask you? So instead, we're going to have agents that have partial knowledge about the classifier. So for example, this is taken from LeetCode. If someone wants to prepare for a technical job interview, they go on LeetCode and they can, I don't know, solve 125 questions about design. And there are also some intersections. So for example, this question belongs to both array and hash table. And what the agents do, they take all of this knowledge and they map it into a prior distribution over classifiers. So for example, they can see that the probability for a question about arrays is going to be 18%. Now, what the learner can do, they can also access this information and they can use it to release a subset. So they can release a subset of classifiers that is going to be true-false in the sense that the actual classifier that is going to be used is going to be part of this subset, okay? And the goal is to maximize the accuracy. Now, this is also the case in Israel, in the Bagruyot, they release a Mikud, where they tell the students which questions are they going to ask. Okay, now, once the agents get this information, this subset, they can compute the posterior. So now, if you consider this subset where the actual question is going to be dynamic programming, then the probability for a question about array is going to be approximately 0.1. And the utility, so previously we had the indicator function here, and now this is going to be replaced with the probability that a classifier which is sampled from this posterior is going to classify them as one. And they're all going to manipulate accordingly. So maybe some agents will only prepare for questions about arrays and strings. Okay. Now, at this point, you might be wondering, why should the learner release anything about the classifier? And we can think about sort of an axis where on one side we have no information, meaning that we release nothing. And this might be protected. And on the other hand, we have full information, which was the classic problem in which we release age. Now, there was this prior work by Galman, Nair, Eilat, Chohen, here, and Rosenfeld that show that releasing age can actually benefit the learner in some cases. And what we are doing is in between. So we are trying to find the sweet spot, which is between the full information where we release age and the no information where we release nothing. Okay, and this is actually helpful. So we show an instance in which if you release the actual classifier, the learner gets a utility strategic accuracy of 0.55. And if the learner releases a subset of size 2, they are getting a perfect utility. So they are getting accuracy of 1, strategic accuracy. So this can actually be helpful. And now we have some theoretical results on this problem. So we start by looking at it from the best response. So an agent needs to best respond. They need to select their optimal manipulation. And we show that the best response is actually NP hard to compute. Now, on the positive side, we show a Oracle efficient algorithm that solves the best response for a class of low-dimensional linear classifiers. And we also show that under natural cost function conditions, there exists an order efficient approximation algorithm for any hypothesis. So this is from the agent side. And now we also study the information release problem. So since the best response is NP-hard in general, here we will only consider agents that are represented by a single feature. Now the manipulation becomes feasible to compute. Now they can all compute their manipulation efficiency. And this assumption also appeared in some prior works. And now I remind you, the goal of the learner is to find the true-false subset that will maximize their strategic accuracy. So here we show that even for this simplified version of the problem, in general, the learner's optimal information release problem is NP-hard. And now we also show positive results. So we show closed form solutions, solution for continuous uniform priors, as well as efficient algorithm for discrete uniform priors. And we also have some results for additional utility functions, such as minimizing false positive and maximizing true positive rate. So this utility function actually make a lot of sense in the context of hiring, because in hiring, what the employer really wants is to avoid hire anyone who is unqualified for the job. And once they do that, they want to maximize the probability of hiring a good candidate. So this is exactly false positive. Minimizing false positive rate is avoiding hiring anyone who is unqualified. And maximizing true positive rate means that we maximize the probability of hiring someone who is actually qualified for the job. Okay, so far so good. So let's talk about learnability. So so far we focused on geometric model, but more generally we can think about more combinatorial setting. Okay. So more generally we can think about combinatorial setting in which each agent is mapped into a node, and then we have a directed edge to a point they can manipulate. So, for example, this could be applying for an additional credit card, and this could be increasing the salary. Both will get them a positive prediction regarding the loan. Now, the agent simply select an arbitrary neighbor, and then we can also, for every instance in the geometric setting, we can map it into a graph setting where if the cost is at most 1, then we will have an edge. And this is going to be easier for us to analyze for learnability. And finally, we're going to assume there is a bounded degree, because not every manipulation is reasonable. Applying for 1 million credit cards doesn't make sense. And since we're thinking about learnability, we will assume that the hypothesis class has a finite VC dimension and little stone dimension, which are complexity measures that are used for learnability. And we have to have finite VC dimension and little stone dimension if we want to learn. Okay. So for example, here, the agent will manipulate either to point 1 or to point 2 because they know the classifier and they know that this is the positive area. And then if this is the classifier, the agent will just stay where he is, because if they can get a positive prediction for free, why move? And finally, if this is the classifier, then the agent will stay where they are, because this is not a reasonable manipulation. And the question I'm going to ask here is, does classic learnability imply strategic learnability? Okay, so we look at various feedback sets. First is the fully informative setting, in which the learner first observes the features before the manipulation, then releases a classifier, and then observes the post-manipulation features. This makes sense, for example, in the context of loan. I might call the bank, ask them about mortgage, they will observe my features. Later on, they release a classifier, and I apply for the loan, and they see my new features. Okay, Second, we look at the post-manipulation setting, which is more aligned with the classic problem, where the learner first releases the classifier and then observes the post-manipulation features. Now, for both of these things, we show a sample complexity bounds. So we study it both in the realizable case, where we assume there exists an hypothesis which is strategic optimal, and in the agnostic case, where we compete with the best hypothesis of the class. And we also derive a regret bound for the online learning problem. And we also look at the feedback setting, where we are in the fully informative case, but instead of assuming that we know exactly what is the manipulation graph, we are assuming it's coming from some graph class. For example, if we are assuming that there are only 10 possible manipulations for each agent, then we will look at a class with a bounded of all the graphs with bounded degree 10. Now, even here, we can still learn. So we derive sample complexity and regret bounds, and most of them are also optimal. And this means that learnability implies strategic learnability. Okay. Moving on, let's talk about what happens in the LLM era. So before I talk about that, in traditional screening schemes, think about the big companies such as Google or Meta. They are getting a lot of applications. So the way they handle it is they run each application through a screening software, which outputs a score between 0 and 100. And then they decide whether to invite the applicant based on the score they are getting. So if the score is above some threshold, they will invite the candidate. Now, the way they optimize for this score is they take the training data and they find a threshold such that solves this optimization problem. So this is maximizing true positive rate such that the false positive rate is 0. Okay, they want to avoid inviting anyone who will be unqualified. And once they do that, they want to invite as many qualified candidates as possible. Okay? So now LLM era, and turns out you can actually use tools such as ChatGPT in order to edit your resume. And this is a completely game changer because it's very easy. Everyone can access it. And ChatGPT alone has 200 million weekly active users worldwide. Now we can also access different levels of LLMs. So you can all access the free version, and you can also pay $20 or $200 extra a month, and then you'll get access to a more to a model with better performance. Now, this means that instead of looking at cost and things, okay, the agent needs to manipulate to the best point, what the agents will do, if they have access to the best LLM out there, then they will just use this, right? Instead of finding what is their best response. So it actually changes the question, and it's more a question of accessibility rather than a cost. And also, because manipulations are stochastic, then, because LLMs are stochastic, then manipulations are also going to be stochastic. So far, all the manipulation were deterministic. Now we can think about it from a fairness perspective. We think that you have two candidates and they have the same resume before manipulation. Now, one of them only has access to the free LLM, and the other one has access to a more premium version. Let's say his mom is using it for work, so she gives him access to it. Now, what happens if we we took 500 resumes and we ran them twice, one time through the free LLM and the other time through a premium version. And then we ran them through a screening software. What happened is that the resumes that were improved by the free LLM got an insignificant score boost, whereas the resumes that ran through the premium LLM got an almost 2 points score boost on average. Yes.
Okay, right? Only change the weight.
Right. We work very hard to avoid hallucinations.
Right.
So there is an applicant. So when I said screening software, I mean applicant tracking system, and there was one that was open source, so we use that.
And it's accepted as entire.
I assume some companies use it, but I don't know exactly. Yeah, but
So some companies use the free screening software and others pay for the premium screening
Exactly.
software.
but the premium ones are also secret because Google don't want to.
And otherwise, that it's very crucial for this study network.
So I can send you the details. I think some companies use it. I don't know exactly. Yeah, I think they also don't want to publish that they use it, right?
It's very central player in the game.
Maybe subsequent folk can be sending these resumes to companies such as Google and see who gets invited. Okay, so as I'm sure you all see, this is in a way unfair. And the reason is that the hirer gets all of these applications and they have no idea which one was manipulated and if so, by which model. And you can think that we have two groups and let's say they have the same underlying unmanipulated resume distribution, but one of them has access to a more to a better LLM. And now this we actually managed to show that this is going to be unfair in the sense that the true positive rate for the privileged group is going to be higher than the true positive rate of the underprivileged group. And this is the most important thing because we are already minimizing false positives. So it means that someone from the privileged group is more likely to be accepted. And specifically qualified workers from the underprivileged group are less likely to be accepted. So this is unfair. And there's also a question of accuracy because at the end of the day, the employer has to select a single threshold and use it for everyone. So what can the employer do? What we are suggesting is a two-ticket screening scheme in which the employer first takes the application, they run it through the most performative LLM for resume editing, and then they are getting two scores, one for the application as it was, and one for the application that was manipulated by the employer. And they invite all the candidates that achieves a score above the threshold for at least one of these applications. Okay, so what we managed to show here is that compared to the to the traditional screening scheme, we improve both fairness and accuracy, theoretically. And also empirically, we improve the accuracy from 55 to 57%, and the disparity between the true positive rate is also improved. Now, yes. Yes, I was just about to tell you. So these are the results just for two-ticket screening scheme, but as Iftaf pointed out, you can also do it more than once. Okay, so since LLMs are stochastic, there is still some advantage for the privileged group where if they have a small probability to pass the thresholds, then they are getting 2 lottery tickets, and the people from the underprivileged group are only getting 1 ticket. So what we show is that we are already improving after running it once, but more generally, what you could do, you can run it more times and technically get into a fixed point. Yes.
But if there is much more advanced model like GPT, they outlook and 2-3 or 1, but and then you get a much more
Better score. So yeah, you're right. And what the hirer can do, like think about the big companies such as Google. They can occasionally test which LLM is the best for resume editing, and then they can just run it as the baseline for the two-ticket screens. Yes.
like itself that you show
Yes. The students are working on that. We have theoretical results for fixed point. I mean, if you run it more times, then eventually it converges, right? The difference between the two positive rates between the groups. So maybe we can talk about this offline. Okay. Okay. So we just showed that it converges. So if you do infinite amount of tickets, then for sure it's fine, right? Like the relative advantage of the privileged group drops every time you run it, right?
But did you check how many operations?
No. Okay. So overall,
I even consider X original, maybe just run it through the LLM.
So this could be problematic, right? If someone really worked hard on their resume and they haven't used the ChatGPT or something similar, it could be that they are getting the best score, and there is every time you run a large language model, the score just drops. So we don't want to discriminate against them, and also, like, think about it. Maybe it doesn't make sense to ignore the actual application, right?
Some companies check on all the
So I'm not sure if this was the case in our experiment, but in general, it could happen. Yes. So so it looks similar if you run it more than once. Like the basic idea is that if you run it through ChatGPT once, and then you take the result and run it again through ChatGPT, the score stays relatively similar. And this is like an observation that we use to get all of these results. No, we ran the manipulation for them, right? So it was a summer project. So no, they're like 2 years old, so we are fine here. Okay. So what I'm trying to say here in this work is that LLMs are complicated, and it is unlikely to straightforward prove anything about them in the next few years. So the way we circumvent that is, first we assume that there is one LLM that outperforms another. We get some theoretical guarantees regarding fairness and accuracy. And to complete that we run some experiment results that validate the assumption, and we also validate the theoretical guarantees using empirical validation. And overall, we get simple theoretical model that still supports what's happening in the real world. Okay, so I talked about these 3 yellow works, and for future work, I'm interested in working on stochastic manipulation for the classic setting. So I worked on stochastic manipulation in the LLM era, and I'm also interested in planning or learning classifiers that will disincentivize manipulations. Okay, moving on, now let's talk about something completely different, which is going to be personalization and explainability. And just for putting things in context, so we said that we as a society care about more things beyond just accuracy, such as personalization and explainability. Okay, and we're going to talk about these things in the context of multi-objective Markov decision process, or MDP for short. Okay, so MDPs are used as a basic model for reinforcement learning, and MDPs and reinforcement learning are behind a lot of the progress in AI in the recent decades. So for example, board games and computer games where we reach human level, if not defeated the world champion in the board games. And now, what all of these games have in common is that they have a single objective. So for example, in chess, the goal is to win, and in other games, the goal could be to maximize some score. The question is what happens if we have multiple objectives? So for example, in investment portfolio, you care about maximizing the expected profit, but you also care about minimizing risk, and there is a trade-off between the two. Another example is commutes. So when you take directions on Google Maps, you might care about things such as worst and average estimated arrival time, traffic conditions, and scenery along the way. Okay, so for a more concrete example, say you need to drive from A to B, and you have two options. One is to drive fast, which will save you time, but you might get a ticket and you might upset your spouse. Second option is to drive slow, and this will take you longer, but it's less risky and you get happier spouse. More generally, when we are thinking about commutes, we can measure some objectives. So for example, the fast car will have a good value for speed, but bad values for comfort and safety. And the slow car will have low value for speed, but better values for comfort and safety. And the way we are going to model these things is with multi-objective MDPs. If you are unfamiliar with MDPs, you can think about them as a finite state automaton where we also have actions. Okay, so we're also going to have transition and reward functions, which are going to determine, based on the action we select, which state we transition to and which reward are we getting. So for example, if we are at state S0, which is going to be the initial state, and we select action A, then we are getting a multi-objective reward 812, and we transition to state S1 probability 0.7, and to state S2 probability 0.3. There's also going to be an horizon, which is the total number of steps in this MDP. And there's going to be a policy which determines which action do we select from each state. So for example, a policy can decide to select action A from state S0 and from state S2, but from state S1, it will select action B. So this is a policy. Yes, let's assume for now, let's assume it's deterministic. Okay, now we also have trajectories. So if we're thinking about commutes, we care about trajectories, right? We care about paths. Okay, we drive from Tel Aviv to Haifa. So let's say we are using the policy I described, and we have our car here. We start at S0, we select action A, and we are getting a reward of 812. And we are transitioning to state S2. And now we select action A, and let's say we are staying in S2. So this means that we are getting a reward of 105. And then let's say we are selecting action A again, because this is our policy. We are getting an additional reward of 105. And overall, for a trajectory of horizon 4, we receive the reward of 10, 1, 12. Okay, now notice that the reward is stochastic when you are using the policy, right? Because you put a transition here and then you get other rewards. Okay, everything clear? So this was our trajectory. And now there's also going to be a value for a policy. So a policy, as I said, is a mapping from states to action. But every policy, for every policy, we can compute a value, which is the expected reward of a trajectory, under the assumption that we are using this policy to select actions. Okay. Finally, we are going to assume there is a do nothing action, which is only available from the initial state, always transitions to the initial state, and has a value 0 for every reward 0 for every single objective. So this is just the car staying where it is. Okay. Now we are going to talk about personalization. So we're going to have user preferences. So each user will be characterized by an unknown reference vector, W star of dimension k, where K is the number of objectives. Okay, so for cars, we have 3 objectives. Now, each user is going to get a personalized value from a policy pi. So this is the inner product between W star and the value of the policy. Okay. So for example, here are the 2 cars for before. If we have a user which is characterized by W star 10, 1, 2, then we can compute the inner products with the values of each of the cars, and we see that this user prefers the first car. Okay. Now, in general, most of the works in MDPs and reinforcement learning consider basic MDPs in which the rewards and values are actually scalars. Now, if we have this single objective MDP, what we can do, we can run a value iteration algorithm, which is well known, and it will return an optimal policy. And this will also be efficient. So we just take the MDP, we run the algorithm, and we get an optimal policy, meaning that this is a policy that will maximize the value. Because here we only have a single objective. We don't have trade-offs. And the question is, what happens when we have multiple, possibly conflicting objectives, and each user has distinct preferences? Okay, so here's an observation. If I tell you W star, you can actually efficiently compute the personalized optimal policy for the user. The way you can do it, you can take W star, you can take the original MDP, and you can replace the reward function, which is now multi-objective, with the inner product between W star and the reward function. Now run value iteration, and you get the a policy which is personalized optimal. So what I'm trying to tell you is that preference elicitation of W star is all we need. Okay, so pi works are focused on approximating the Pareto optimal solution set. So this is a set of policies such that if you improve on one value, you sacrifice another. You want the car to be faster, this is going to cost you with safety. And then our goal is to find optimal personalized policy for a user with unknown preferences over the K objectives. Now, there was one other prior work that considered preference elicitation, where they consider linear preferences like we do. And they had a query model that provides stochastic feedback on a single policy. So if the fast car has a personalized value of 102 for the user might say something like, for me, the car is 104. Now, for us, it's a bit strange. Think about your commute to Tel Aviv to university today. What was the value from your commute? Can you actually give me a value or a number? So, okay, so we consider the more natural and intuitive query model, which is comparison queries. So in our model, we show the user 2 cars and they select which one they like more. Okay, more formally, if there is enough difference between the values up to some parameter epsilon, then the user tells us which policy they prefer. And if not, they say indistinguishable. Now, this is taken from ChatGPT just to show you that this feedback is very intuitive. So if you get an additional response, then they ask you whether you like the other response better, worse, or the same. This is exactly the same model. Okay. Now, a few observations before I describe the idea of the algorithm. So first, if we use the do nothing action, we can actually generate a do nothing policy, right? So this is a policy that will always stays in the initial state and gets a value of 0 for every single objective. Second, if we take the set of achievable value vectors, this is going to be a convex set. And the reason is that we can mix policies. So we can still think that pi 1 is going to be deterministic, but we can use pi 1 with probability 50% and with probability 50% use another policy. Okay, so I have 2 cars, probability 50% I use this car, probability percent I use this car. Now we're going to assume that the rank of the span of the value vectors for a specific MDP is going to be of rank K. It's going to have a full rank. Okay, I'm just going to describe the high level ideas here. So let's imagine for a moment that we have two things. First, we have a basis of policies. These are policies pi 1 to pi k, such that their values is a basis in the linear algebra sense of the word for the span of all the value vectors. Okay, so this is a set which is achievable by any of the values that are achievable from every possible policies on this entity. That's a good question, and I'll answer it in a few slides. And now we are going to use pi 1 as a benchmark policy. And then again, we are assuming we have this basis of policy. Now let's assume that we have basis ratios. So these are ratios between every policy pi 2 to pi k compared to pi 1. Okay, so for example, we know that the user prefers the first cow twice as much as the second cow. Let's imagine that we have that. So this will give us k minus 1 equations with k variables. And to complete that, let's assume that the L1 norm of W star is 1. So this will give us additional equation. And now we have k equations, k variables. We know how to solve this. Everything is great. We can solve for W star. And once we know that, we can compute pi star, the personalized optimal policy for the user. Okay, everything is great. What the problem? I just said imagine. So this is not going to be that easy. User, for example, will not tell us, I prefer the first cow twice as much as I prefer the second. We are going to have to get it from the user. And the way we're going to do it is using comparative queries. We're going to take the basis of policies, pi 1 to pi k. And we are going to find these ratios between pi 1 and any other policy. So we start with which do you prefer, policy 1 or policy 2? And let's say the user prefers policy 1. What we can do now is mix it with the do nothing policy. And then reduce the value. We multiply the value of the first cow by half. And then we ask the user, which one do you prefer? 50% of policy 1 or policy 2? And then we run it as a binary search. And we stop once the user tells us indistinguishable. Okay, so for example, here, the ratio between the first cow and the second cow is 0.5. The user prefers the first cow approximately twice as much they prefer the second cow. And the reason why it's approximately is that we can only compare up to epsilon. Okay, there are going to be some cows such that one is better than the other, but the user cannot tell the difference. Now, since we have estimations for this means that we will need a good basis of policies. Now, you asked earlier whether it's easy to find. So we all know how to find the basis in linear algebra, but here all we have is the MDP. And even if you take, so we show an instance in which if you take 3 policies such that each maximizes a different objective, what you are getting if you take their span is a space of rank 2, where the actual rank is 3. Okay, so it's not even easy to find the basis. Now, more importantly, even if we find the basis, we want the equations to be well conditioned. We want to control the condition number. Okay, so let me show you an example. If we have a user which has a preference vector of 1, 1, 1, and we take this, which is a basis in the linear algebra sense of the word, then we get the alpha, which are going to be 1. So if you compare these two, the user will say indistinguishable, and if you compare these two, the user will also say indistinguishable. And now, what will happen is that we will return a policy, for example, 500, which is going to be very far for the personalized optimal policy for the user, which is perhaps this, right? This is very different. Okay, so the additional challenges is that we need to find a well-conditioned basis. Okay, so we have a theoretical guarantee here that if we use the algorithm, then using k log k over epsilon comparison queries, we output a policy which is nearly personalized optimal for the user. And notice that since we are using binary search, this is the bare minimum of the comparison queries that we need. Okay, moving on, let's talk a little bit about explainability. So far we described policies as a mapping from state to action. It doesn't make sense. If you're thinking about cars, if I give the user the code of the car, so I know that the car will turn left if I'm here, and will accelerate if I'm here, and stop if I'm here, it doesn't make a lot of sense in the context of things such as speed, comfort, and safety. This could be a very long list. So instead, we can think about something more intuitive, so perhaps trajectories. And so trajectories are interpretable, right? I'll show you a commute with the cars. This will be interpretable. But the thing is, even if we sample enough trajectories, so in the computer science sense of the word, then with high probability, we know that the reward will be close. But the thing is, if we are thinking about applications such as safety, then this would be a problem. Because if the car has a probability of 1 in a million for an accident, and we have a user who cares about safety, we might not capture it even if we sample enough trajectories. So instead, we are providing a solution, which is a representation for a policy. So each policy is represented by a set of weighted trajectories, such that if you take the reward of the trajectories, according to the weight, if you take this expectation, this is going to be exactly the value of the policy. So, for example, if we care about cars that drive from your home to the airport, instead of showing you this complicated code, what I can ask you is that, what do you prefer? A car that takes a specific route, and with probability 90%, it takes you 40 minutes, and probability 10%, it will take you 3 hours because there is an accident. Or I will show, or do you prefer the alternative policy, which is taking the subway, which always has a duration of an hour? Now I can ask you this, which one do you prefer? And this will be interpretable and exact. Okay, so the question is whether such a set even exists, and if so, how to find it efficiently. Now the existence follows from Cartier-Doris theorem. So the way to do it is, we can think about all the trajectories in the support of the policy, and each trajectory has some reward. We can put them as a point in some space, and then we can take a convex hull. So we take the convex hull, and now what we know is that the value of the policy is actually inside the convex hull. So this is because the value of the policy is the expected reward of the trajectory of the trajectories, assuming that we are the points. The points are the rewards of all the possible trajectories.
Oh, it's your reference there.
So you remember the red car that drives, and I showed you one trajectory. It had a multi-objective reward.
Yes.
This is 1 point. Now,
Meaning the space is this, the dimension is the number of
objectives, assuming it's full, yes. Okay. So we take the rewards of all the trajectories, we take the convex hull. Now we know that the value is inside the convex hull. And using Cartier-Doris theorem, we know that as a point inside the convex hull, the value can be represented as a convex combination of at most k plus 1 vectors from the black points. Okay, now this is still not going to suffice, and the reason is that Cartier-Doris theorem, if you just apply the proof behind the Cartier-Doris theorem, it doesn't take into consideration that all the points are coming from the same MDP. What we are doing, we are providing a solution which is more sophisticated and is based on the inherent structure of the MDP. And we get a polynomial time algorithm to find this set. Okay, any questions? So for future work, I'm interested in keep working on the intersection of machine learning theory and societal challenges. And I already described what I'm going to do in strategic classification. But here is a glimpse of what other possibilities are out there, at least for me. So I also worked on personalization in the context of recommender systems. And here there is an interesting problem called the filter bubble effect. So this is where recommender systems, they learn from user data. And this might reinforce bias or radical ideas. The reason why it happens is that they want to show content that the user likes. And as such, they might reduce exposure to diverse content. So this problem is called filter bubble. And for example, in 2016, a lot of people were surprised by the fact that Trump won. And the same happened in Brexit. So the challenge here is to balance personalized recommendations and diverse content to avoid filter bubble problems. Okay, another big problem that I'm interested in and worked on in the past is algorithmic fairness. So as you all know, algorithms are now used to influence jobs, loans, and so on. And I'm interested in looking at it from a higher level. So, for example, it could be the case that if 5 firms are looking, if we have 5 firms and each looking to hire a single candidate, they might all use the same algorithm. And if the algorithm has predictions, then they might all offer a job to the same person. Now, this is problematic both in terms of accuracy and fairness, right? This person can only go to one place, and the rest of the candidates that could also be very qualified and get a very similar predictions are not getting even a single offer. So this problem is called algorithmic monoculture, and it was introduced by Kleinberg and Ragavan. And they studied it from a game theory perspective. And my goal is to study it from a learning theory perspective. Okay, so before I finish, I would like to thank all of my wonderful co-authors. And I know I showed you this before, where all of my works are here on this pipeline. And this is the societal questions. Now I want to show you from a different perspective. So in problems that relate to incentives and learning, this is a strategic classification. These are the work I talked about today. There was an additional work I haven't talked about. And then this is the work I talked about in the context of personalization and explainability. And I also work on incentivized collaborative learning. I have other works on personalization, algorithmic fairness, explainability, and other societal constraints. And that's it. Thank you very much.